Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 3 from the course, but make sure you have watched the previous ones before viewing this one. In the last lecture, we had started our discussion about the discovery of the fundamental particles, wherein we completed the discussion on the discovery of electron. In this lecture, we would be continuing our discussion of the fundamental particles and we would be discussing the protons and neutrons. So now it was known that there are negatively charged electrons as an essential constituent of all atoms, and the atom as a whole is electrically neutral. So there had to be some positively charged particles present in the atom which neutralize the negative charge on the electrons. The presence of the positively charged particles in an atom was shown by Goldstein in the discharge tube experiments. So this is a diagram which was the apparatus used by Goldstein. It is essentially the same cathode ray tube, but the only difference here was that he now placed a perforated cathode and a phosphor screen behind the cathode. So now what was seen was that there was a red glow seen behind the cathode also when the voltage was high and the pressure was reduced. So from this we could infer that there was a stream of particles traveling from anode to the cathode, passing through the perforations and making the wall glow. Goldstein called these particles as canal rays, and they were later known as positive rays or anode rays. Positive rays because the nature of the particles of these rays was positively charged, and anode rays because the direction of the particles was from the anode towards the cathode. And now the study was made with different gases, and when hydrogen as a gas was taken, the positively charged particles found were to be the lightest particles, and when other gases were taken in the discharge tube, the masses of the positive particles, they were found to be whole number multiples of the mass observed for hydrogen atoms. This led them to think that positively charged particles, basically they are made up of a combination of the particles of hydrogen. So the fundamental particles of hydrogen were named protons by Rutherford because of the Greek word proteos, meaning of first importance. So the fundamental particles of hydrogen, they were considered to be of first importance, found to be the essential constituent of all the gases, all the positive particles that were striking. So the name proton. So the properties of these positive rays or the anode rays essentially quite similar to that of the cathode rays. First being that the anode rays travel in straight lines and cast the shadow of the object placed in their path, showing that these rays had particle nature and they travel in straight lines. So these rays affect the photographic plate and cause fluorescence, that is the flash of light or scintillation, and then they rotate a paddle wheel placed in their path, again showing that these had a particle nature and a high kinetic energy. Then they heat the metal on which they fall, showing they are highly energetic. And then the difference from the cathode rays comes here, that these rays when deflected by the electric and the magnetic field, they move in a direction opposite to that of the cathode rays, showing that these rays are positively charged. So in the electric field, basically they are going to be deflected towards the negatively charged plate, and similarly in the magnetic field the direction is opposite to that of the cathode rays. Hence these rays were shown to be positively charged. And then the E by M ratio is not the same for all positive rays, and they depend upon the nature of the gas in the discharge tube, showing that these rays, they were not consisting of electrons but something else. So next we have the few characteristics of protons. So basically proton is nothing but a H positive ion. So this is a positively charged particle with the same magnitude of charge as that on an electron. The electron had minus 1.602 into 10 power minus 19 coulomb charge. So the proton has plus 1.6 into 10 power minus 19 coulomb charge. Then the mass of the proton is called as unit mass, and this is 1.672 into 10 power minus 27 kg, and this is 1837 times the mass of an electron. On the atomic mass unit scale, the mass is 1.007276 AMU, where 1 AMU is 1.66 into 10 power minus 27 kg. And the number of protons in a neutral atom is equal to the number of electrons in it. So the number of protons, this is denoted by the symbol Z, and it is called as the atomic number. So this is important. Please remember that in a neutral atom, the number of protons is always going to be equal to the number of electrons in it. The E by M ratio of a proton is 9.58 into 10 power 4 coulomb per gram. This is the E by M ratio of proton or the hydrogen ion H positive, not for all the gases which were taken in the discharge tube. Please remember that the E by M ratio of the positive rays or the anode rays is going to be different depending upon the nature of the gas taken. And now, where did these anode rays originate? Well, these basically originate in the discharge tube. The cathode rays, if you remember, while they were traveling from the cathode to the anode and they were striking the gas particles present in the discharge tube, they being highly ionizing, they knock off the electrons from the atoms of the enclosed gas, which form ions, right? So the atoms of the gas, the electrons have moved out from those atoms. So what is left behind? Left behind is nothing but a positive ion. And now this positive ion is basically what it is going to be, the atom of the individual gas which has lost the electron, and hence that is why the mass of each of this positive ion has to be different. So being positively charged, these ions, they move towards the negatively charged cathode. However, unlike the cathode rays, please do remember that these rays depend upon the nature of the gas enclosed in the discharge tube. And I hope I am clear about this. This is one important point which is frequently asked in the examinations. And now we can define the proton to be a subatomic particle having unit positive charge and unit mass, which we've already discussed. This is about 1837 times the mass of an electron. So now we have finished with the discovery of two fundamental particles, the electron and the proton, and we are left with the discovery of one fundamental particle more, which is important, and that is the neutron. But before moving to the discovery of neutron, let us discuss one more topic, that is the discovery of radioactivity. And why? Because this is a phenomenon that supports the divisibility of the atom. So there are atoms of some elements which, for example, like uranium, thorium, polonium, radium, which are unstable, and they spontaneously disintegrate with the evolution of certain invisible rays. And the existence of these rays was discovered by Henry Becquerel in the year 1896. Actually, he was studying the phenomenon of X-rays, which was discovered in 1895 by Wilhelm Röntgen. And so while studying this, he noticed that uranium salts cause the photographic plates to blacken even when they were wrapped in usual light-proof paper. So this is how he discovered radioactivity. So what is radioactivity? It is the phenomenon of spontaneous emission of invisible radiations by some elements. And the elements which show this radiations, they are called as the radioactive elements, and the radiations are called as the radioactive radiations. The term radioactivity was coined by Marie Curie in 1898, and what she was basically doing was that she was also studying the phenomenon of radioactivity, taking uranium, and this had already been discovered by Henry Becquerel, and she and her husband both were studying, and what they were doing was basically they had taken a uranium ore which was pitch blende, and then they were separating out pure uranium from the ore. What they found out was that the left out uranium ore was more radioactive than expected. And this led to the discovery of two more radioactive elements, radium and polonium, by them from the remnant of the uranium ore which they had taken. So radium, this was found to be a million times more radioactive than uranium, and at present more than 50 naturally occurring radioisotopes are known to us. One important piece of information, that radioactivity of an element, it is not affected by physical factors like temperature, pressure. Nothing is going to happen. They just spontaneously disintegrate. We do not require a high temperature, we do not require a pressure to cause the phenomenon of radioactivity. It is a natural phenomenon, and then it is not even affected by chemical combination. So the radioactive element, this is going to exhibit radioactivity even in the free elemental form as well as in the compound form. So now let us study what is the nature of these radioactive radiations. Well, these rays which were being emitted by the radioactive elements, they consisted of three types of radiations, and there was a experiment done to show that there were three types of radiations. This consisted of keeping a small portion of a radioactive substance in a thick lead box with a small hole, and then the radioactive radiations from the source, they were allowed to pass through a small slit so that only a narrow beam of the radioactive rays could pass through, and then this was subjected to an electric field, a positive and the negative plates of a very strong electrostatic field. And what the experiment showed was that this beam, it split up into three different types of radiations. The radiation that got deflected towards the negative plate of the electric field showed that it was positively charged, is called as the alpha radiation. And then the radiation beam that got deflected towards the positive plate, that is called as the beta, and the one which did not get deflected, was not carrying any charge, that is the gamma radiation. So here one which is getting towards the positive place, it is the beta radiation, one which is getting deflected towards the negative is the alpha, and one which did not get deflected, that is the gamma radiation. So then after the discovery of the alpha, beta and the gamma rays, further study was done about the nature of these rays by Rutherford, and he found that the alpha rays, they consist of high energy particles carrying 2 units of positive charge and 4 units of atomic mass. And he concluded that the alpha particles are nothing but helium nuclei, as when the alpha particles, they combined with 2 electrons, they yielded the helium gas. So helium is basically having 2 protons, that is the atomic number is 2 and the atomic mass is 4. So if we take out 2 electrons from it, what we get is an alpha particle, right? An alpha particle, combine it with 2 electrons, you get what? The helium gas. So this is what he found out, that alpha rays, they are nothing but the helium nuclei. And then beta rays, they are negatively charged particles which are similar to the electrons, and the gamma rays, they are high energy radiations like the X-rays. They are neutral and do not consist of particles. The alpha particles, they are the least penetrating, followed by the beta rays and then the gamma rays. So now let us see how the neutron was discovered. Well, we now know, and by that time when the discovery was being done, it was known that the atoms, they are electrically neutral and they consist of an equal number of protons and neutrons in a neutral atom, right? And then there was an experiment done by Rutherford and his students called as the alpha ray scattering experiment, which we would be doing in the next lecture, where he found that the whole mass of the atom was concentrated in a very small portion called as the nucleus of the atom. And hence, as the electrons, we know they have a negligible mass. So what Rutherford and his students said was that the protons, they are basically present in the nucleus, and the electrons, they are moving around this nucleus. Okay, so Rutherford, he was able to calculate basically the how much positive charge is present in the nucleus, or you can say he found out the number of protons in the nucleus of the atoms. So when they calculated the nuclear mass based on the number of protons, the value always fell short of the actual mass. What do I mean by that? We basically, when they saw that the mass of the hydrogen atom, so mass of the hydrogen atom was equal to the mass of the proton, because hydrogen has 1 proton and 1 electron. Then they saw the mass of the helium atom. So helium basically has 2 protons as compared to the 1 in hydrogen. So the mass of the helium atom should have been twice that of the hydrogen atom. But that was not the case. Actually, it was 4 times that of an atom of hydrogen. So this was also seen in other elements also. So the thought was that there is something present in the nucleus along with the proton, which is electrically neutral but contributing to the mass of the atom. And these particles, they were discovered basically experimentally by a scientist called as Chadwick. And what he did was that he bombarded a thin sheet of beryllium with alpha particles. So alpha particles are basically helium atoms which have lost 2 electrons having a +2 charge. And when these alpha particles strike beryllium, they produced what? An electrically neutral particle which was having a mass slightly greater than that of the proton. And these particles he called as neutrons. So let us see the reaction. Basically, this is helium. Okay, so helium, or the alpha particle, which has +2 charge and the mass of 4 uh, AMU, and then this was bombarding the beryllium atom with the atomic number 4 and the mass number 9. And then what was being formed was a carbon atom with atomic number 6 and mass number 12, and a neutron which had no charge and mass of 1 AMU. Right? So this is how the neutron was discovered. Another experiment, similar one, where boron was bombarded with the alpha rays and formed was nitrogen and again a neutron. So this is how the neutron was discovered. And now, after the discovery of the neutron, it was found that the nucleus of an element consists of protons and neutrons, and collectively they are called as nucleons. The mass of a neutron was also calculated, which was 1.675 into 10 power minus 24 grams. This is slightly higher than that of a proton. So now we can comfortably define a neutron to be an electrically neutral subatomic particle having mass 1.675 into 10 power minus 27 kg, which is nearly equal to that of the hydrogen atom or the proton, slightly higher mass. So now, another point which you will realize later also, but worth mentioning here is that the number of neutrons in the nucleus of an atom is nearly equal to the number of protons for the first 16 elements, after which the number of neutrons is generally greater than that of the protons. And all the elements except hydrogen, they contain all the 3 fundamental particles, that is, they all contain the proton, electron and neutron. It is only the hydrogen atom which has 1 electron, 1 proton and no neutron. Now the properties of the neutrons. This one is already clear, I think. It is a neutral particle with mass 1.675 into 10 power minus 27 kg, making it the heaviest of the 3 fundamental particles. Then a few free neutron, this decays into a proton with the emission of an electron and a neutrino. So what is a neutrino? Basically, it is a particle of negligible mass, almost zero mass and zero charge. Okay, so this is what is a neutrino. We have the reaction in front of you. The neutron, this basically decays into a proton, electron and neutrino. And then the neutrons, they are highly penetrating, but they are less penetrating than the cosmic rays. Cosmic rays are basically generated in the outer space, not on Earth. But the neutrons, they have to be found to be less penetrating than the cosmic rays, but still they are highly penetrating. And then they cause the emission of high-speed protons from hydrogenous material like water, paraffin, cellophane, etc. And this property has been utilized to measure the energy of neutrons. Unlike X-rays, these do not cause ionization of the material through which they pass. Then we have the types of neutrons. This is basically based on the energy they have. So the first we have is the thermal neutrons, then we have epithermal neutrons, and then fast neutrons. So thermal neutrons, basically these are having a thermal equilibrium with the matter through which they pass, and they have a Maxwellian distribution of energies with the most probable value depending upon the temperature. Basically this line you will be able to understand only when we do a course called the states of matter. For now you can just keep it in your notes, try understanding it when we come to the topic states of matter. and the most probable energy of the thermal electrons at 27 degrees Celsius is 0.00160 electron volt. And then we have epithermal neutrons. The energy increases. It is between 1 electron volt to 1.2 mega electron volt. And then fast moving electrons, they are having energy greater than 1.2 mega electron volt, and this is the minimum energy which is required for the fission of uranium. But please do remember that slow neutrons, they are more effective in causing fission, because the high speed neutrons, they may pass through the nucleus without bringing about the transmutation. So next we have the uses of neutrons. The first being that the neutrons are used for the transmutation of elements. So if you remember the course Some Basic Concepts of Chemistry, wherein we discussed nuclear reactions under the heading types of reactions. So the nuclear reactions, what is basic feature is that the identity of the elements is lost. One type of elements, they are getting converted into another type of element. So this is what we mean by the term transmutation of elements. So here neutrons play an important role, and some of the elements, they require fast moving neutrons for the transmutation, whereas others require slow neutrons. For example, we have a nitrogen nucleus, this being bombarded by a fast moving neutron to eject an alpha particle and the formation of a boron nucleus. So the reaction is for you. And then we have certain nuclei which can capture slow moving neutrons with the emission of gamma rays, and the new substance formed are radioactive. So this is the other reaction. Here copper 65, this is the normal isotope of copper. Copper 65 and copper 63, they are two stable isotopes of copper, and this, on capturing a slow moving neutron, forms copper 66, which is radioactive. Copper has around 27 radioactive isotopes, and this on further decay is going to form zinc 66, which is the normal zinc isotope, right? So basically neutrons, they are used for the transmutation of elements, and then certain nuclei, due to their intense biological effects, they are now being used in the treatment of cancer. Now we just briefly see which are the uncommon fundamental particles. A few of them, if you remember, we started with the lecture of the discovery of the fundamental particles, that there are around 35 subatomic particles being discovered till date. So just a few of them. We have, first is the positron. We have denoted this by E with the 0 as the mass and +1 charge. So basically this is the positive counterpart of the electron, having +1 charge equal to that of the electron. Electron has -1 unit charge and no mass. So this was discovered by Carl Anderson in 1932. These are highly unstable. They combine with electrons producing X-rays. And then we have neutrinos and antineutrinos. They are particles of small, nearly zero mass and zero charge, and they were postulated by Fermi in 1934. Next we have the pi mesons and the mu mesons. So they are positively or negatively charged particles, and they have a mass intermediate to that of the electron and the proton, and they were postulated by Yukawa in 1935. And then we have neutral mesons. These were postulated by Kemmer to account for the binding forces between the like particles, such as proton and proton and neutron and neutron. So now we have basically a chart to just recapitulate what all we have discussed about the fundamental particles. So here we have the electron, the symbol for the electron, and then electron was discovered by Sir J.J. Thomson, proton by Goldstein, and neutron by Chadwick. and then we have the atomic mass unit scale mass for us in AMU, and then in grams the mass of the electron, the proton and the neutron. The electron being have a negligible mass, and then proton and neutron, they having almost same mass, the neutron being slightly heavier. And then the charge, basically the electron has minus 1.602 into 10 power minus 19 coulomb charge. The proton same charge but plus 1, and this on a relative scale we are saying as this being the smallest charge possible. If you remember, we had said that this is denoted as minus 1 charge. And similarly the proton, the positive part of the same charge, we call this as plus 1 charge, and this is given in the ESU. And the neutron, this does not have any charge. And now what is the location in the atom? Electron is outside the nucleus, the proton and the neutron, they are present inside the nucleus, and collectively they are called as the nucleons. Now the have and edge section, just to quickly recapitulate what all important points we have discussed about the neutron. So neutron was discovered by Chadwick. Isolated neutron is unstable and it disintegrates into electron, proton and neutrino. And then we have 1 unit charge, that is equal to 4.8 into 10 power minus 10 ESU, or 1.602 into 10 power minus 19 coulomb. And then 1 AMU is what? This is 1/12 the mass of a C12 atom. And some extra facts about the neutron. The mass of the neutron 1.675 into 10 power minus 27 kg. Specific charge 0. The density is 1.5 into 10 power 14 gram per cubic centimeter, and the mass of 1 mole of neutrons is approximately 1.008 gram. That would be all for this lecture. I hope you enjoyed studying the discovery of the proton, the discovery of radioactivity, as well as the discovery of neutron with me. I really had a nice time, and if you had, so please do click on the like link, and also do subscribe to our channel by clicking on the subscribe link and the bell icon, so that you get a notification as and when we put up a new lecture for you. For any queries you have, any suggestions you want to give to us for the betterment of our lectures, please feel free to mail us at h2ochemistry@gmail.com. We would meet again for lecture 4 on the topic atomic models in the course the atomic structure on the channel H2O. Bye for now. Have a nice day. Enjoy yourself.